Okay, great. So I believe that's the recording started. Good morning, everyone. Welcome to Superconductivity Lecture 6. We're past the halfway point just of the, shall we call it the initial block of 10 lectures? But I should warn you that I've got quite a bit of travel in May, so we can't just extend straight into the early weeks of May. But if we need more, we'll figure out some time to do more. But we did at least get as far as superconductivity. So to remind you of what we discussed last time, we talked about basic phenomena of superconductivity, perfect conductance, the Meissner effect, the signature in the specific heat capacity. And we pointed out that several aspects of that are quite different from what we had in the superfluid. In particular, simple superconductors are fully gapped. There are no low-lying excitations at all, which is quite different from the superfluid that had the Bogoliubov sound modes. And we talked about writing an effective free energy for the superconductor along similar lines to the superfluid, assuming there is still some kind of complex scalar order parameter. But we immediately discovered that because that's now charged and we have to couple it to the electromagnetic field, the physics that results is quite different. And we spent some time discussing the fact that what used to be a physical rephasing symmetry of the order parameter is now a gauge symmetry of the whole theory. And so we don't have those sort of independent different phases. But we can still write a Landau-Ginzburg type free energy. And the idea is in this lecture to kind of use that to make some predictions about what we will see, and in particular to predict the Meissner effect, the expulsion of magnetic flux from the bulk of the spot.
And for completeness, we also established then that the second order phase transition, that is the superconducting transition, does not conform to the Landau theory of phase transitions.
That's correct, or at least not the Landau theory of phase transitions with a regular zero-form local order parameter. In some deeper sense, it kind of does. The high-temperature phase breaks a one-form symmetry that the low-temperature phase restores, but the fact that that's a one-form symmetry and is about strings means it doesn't fit within at least the conventional version of the
Okay, but I would have thought that the conventional theory of Landau was associated symmetry breaking with the formation of an order parameter, right? So isn't what Landau wrote down in the late 30s about the breaking, it's the wrong way around.
Yeah, no, I agree. So if you refer to psi as the order parameter, then that is different from what you'd expect from Landau's theory, because you should have the order parameter in the ordered phase. Yeah, agreed. Good. So let me rewrite the free energy that we're using. So the free energy of the superconducting phase as a function of temperature is some normal part that we're not really going to think much about, plus some integral over space of a gradient part. We'll continue to use this suggestive form for the prefactor. And the point is that now, because the field is charged, we have to have this vector potential part attached to the gradient. So we attach that to the gradient, then take the gradient of the order parameter field, then take the square modulus, and then everything else is much as it was. We have a term which, when it goes negative, prefers to develop a modulus of the order parameter, and we have a term that keeps that modulus under control. And then we also have the integral over space of the square of the magnetic field strength divided by 2 mu naught, which is just the Maxwell energy of the field in the space. As pointed out previously, we should regard this as now a theory for the two fields that are involved, the superconducting order parameter and the magnetic field. And because of gauge invariance, we can't really pull those apart. So I'll be, in fact, one of the things we're going to do in this lecture is to completely rewrite this deep in the superconducting phase in terms of only what the magnetic field is doing, because that's the most efficient way to derive the Meissner effect.
Deep in the superconducting phase, but then are we able to use the Landau-Ginzburg expansion?
Right. I mean, I guess what I mean by deep in the superconducting phase is considering only fluctuations of the phase of the complex order parameter and not its amplitude. That doesn't really require you to be deep in the superconducting phase. Amplitude fluctuations always cost you more than phase fluctuations. It's just that that effect becomes stronger the further you get from TC. So the hope is that there's some region where this truncation will work, but where the amplitude fluctuations are sufficiently damped out that we can just think about phase rotations. There's one other point I wanted to make, because this always used to confuse me. This integral, if you like, runs only over the superconducting sample. You could say that it runs over all space and that outside the superconducting sample the order parameter is 0 anyway. But since the order parameter is 0 outside the superconductor, this basically runs over the material. This runs over all space. And this is crucial for thinking about the Meissner effect. Because if I only ran this integral over the sample, there would never be any energetic incentive to admit a magnetic field, right, however strong your boundary conditions became. So we'll discuss that when we come to the Meissner effect, but I just want to highlight that at this point. There's a distinction between this bit of the free energy and this bit, because this bit requires integrating also over the region outside the sample. Okay, so can we derive the Meissner effect? And this is a counterexample to the statement that whenever there's a question in the title, the answer is no. In this case, the answer is yes, we can derive the Meissner effect. So, suppose fluctuations of the modulus of the superconducting order parameter are negligible, which is generally a reasonably good approximation unless the boundary conditions force some difference from that. In that case, we should be able to write this complex field as some position-independent amplitude, which I'll write conventionally as root ns over 2, ns being the superfluid density, and then all the action will go on in this phase. Now remember, as we've discussed, that phase is not a gauge invariant quantity. However, you can't write down anything in this theory without writing down something which is not gauge invariant, so I'm going to write that down, but just make sure that the observables that we derive are gauge independent. So it follows from that that the gradient of theta, which is also not gauge independent, is I root ns over 2 times grad theta times e to the I theta.
You mean gradient of psi?
Yes, sorry. Yeah, the gradient of the scalar order parameter is proportional now to gradient theta. Thank you. And if I substitute that into the free energy expression, I get that the difference between the superconducting and normal free energies is the integral over space of ns over 4 m star times h bar grad theta plus 2 ea squared. I've brought the h bar inside the bracket to make this look more like a momentum. And of course we still have the b squared over 2 mu naught piece. And then there's some constant, which is just the condensation energy of the superconductor, but we don't care about that because it doesn't depend on the phase. Right, so that came from these two terms. So in this regime, basically the free energy simplifies to something which depends on what the order parameter phase field is doing and something which depends on what the field is doing. Now, it turns out that this term here is intimately related to the current density of the superflow. So we can compare to the expression for the supercurrent. If we go through the sort of Noether's theorem argument that we went through last time, we can derive, well, we didn't go through it last time. I told you that if you go through it, you get the thing I'm writing down. I'm going to say exactly the same today. If you go through it, you get the thing I'm writing down. So the current from the superflow, which is the only current we have at these low temperatures, is minus NSE over M star times exactly this quantity that we have in the brackets, h bar grad theta plus 2EA. I've carefully written this in a gauge invariant form. If you apply the gauge transformation that we discussed last time, right, so the phase goes to a phase plus chi, so that pops out a grad chi here, but phase goes to phase minus chi, but A goes to A plus grad chi. So this is a genuinely gauge invariant expression for the supercurrent. And it should remind you of the supercurrent that we got in the superfluid case. In that case, we had only this first term, but otherwise things look very similar. So in the superfluid, we were able to say that the supercurrent is just the gradient of the phase. We now can't say that because that wouldn't be gauge invariant. The gauge invariant combination is to say that it's the phase gradient plus the vector potential. We could pick a gauge in which the first term disappeared, and then we would just have that the current is proportional to the vector potential, and sometimes you will see that equation written. And that's just adopting a particular gauge where all of the supercurrent comes from the electromagnetic field and none of it comes from the phase winding of the order parameter.
That's the London gauge.
That's the London gauge. But that's a pure gauge choice, and I think it's clearer to just write down the gauge invariant expression. It also connects back more nicely to the superfluid, because if I were able to keep A equals 0, then this would just be the superfluid expression. Okay.
Can you have a superconductor without a magnetic field, so that in this case you would have an expression that's similar to the superfluid?
The problem is going to be that that wouldn't be consistent, because as soon as I start running a current, I will have a magnetic field by Ampere's law. So in some kind of leading order, maybe, but if we're going to have finite currents, they will cause finite fields. And so that's all in the same area of the sample, so I kind of have to talk about them both.
Although Ampere's law is not part of your theory yet, is it?
It is, yeah, so Maxwell's equations are part of the theory here, I'm going to be, I mean, they come from extremizing gradient terms for the field that I haven't written down. So yeah, for simplicity, I haven't included those bits. I'm just going to say they give rise to Maxwell's equations, and so Maxwell's equations will apply. Yeah.
So just be careful. Now we're doing the integral over all space, but also could we have that the phase is non-zero outside the sample, even though the order parameter goes to 0 because the density is 0?
Yeah, okay, that's a fair point. So there's an issue about edges of the sample here because, yeah, I mean, the thing is that very near the edge of the sample, the approximation we've made is going to fail anyway, right? Because what we've said is the amplitude is not varying in space. If we're going to get from a bulk of the superconductor where mod psi is a non-zero constant to outside the superconductor where mod psi is 0, then clearly it's going to have to vary in space. So actually, we're sort of assuming a result that we're going to talk about later, which is that at least in certain superconductors, the magnetic field varies on a much longer scale than the superconducting order parameter. And so I'm sort of picturing that the superconducting order parameter is basically jumping to 0 at the edge, even though I told you earlier that wasn't possible and it's not really true. Right? But on the length scales that we'll be concerned about, it's more or less true. Yeah.
But so is the integral over all space or only the sample?
Now the integral has to be over all space, but on the understanding that I ignore this term.
Okay, yeah.
So yeah, I mean, really I shouldn't write this as a single integral, but I mean what I meant before, that this is integrated over the sample and this is integrated over all space. But it turns out we're only going to use the resulting equations inside the sample, so that's not going to matter so much in this bit of the discussion. Okay.
So,
Yeah.
but the argument we have for the superfluid with the healing length should still be true, right?
Yeah, that's right. So this still has a healing length, and so it will still be the case that actually the order parameter takes a distance of that healing length to recover from the edge of the sample. So what I'm implicitly assuming, for the sake of an easy demonstration, is that any length scales that characterize the magnetic response are going to be much longer than that, and therefore I can more or less think of it jumping to 0 at the edge.
But then it's fine, right? Because we get the length scale, I guess, for the magnetic whatever, and then if it's larger, it's fine.
Yeah. Actually, what we'll find is that sometimes it is and sometimes it isn't. So really, one would have to go back and do this more carefully if the superconductor were type 1. But details. Yeah. Any other questions? Okay, so what I'm going to do now is to just put that into my free energy expression. So I'll call this superconducting normal difference delta F. I'm going to drop this constant because for our phase considerations it's not going to matter. And then what I have is the integral over space with the caveats given before. And this first term can just be written m star over 4e squared superfluid density times the square of the physical current. And this term is 1 over 2 mu naught times the square of b. And now I can go a step further and say, well, look, I know from Ampere's law, which is one of Maxwell's equations, that curl of B is mu naught J. So I can now actually remove the current from this expression and replace it by the curl of the magnetic field. And if I do that, I get, bringing out a 1 over 2 mu naught, an integral over space. So the current term becomes m star over 2 mu naught superfluid density times e squared, and now I replace the current by the curl of B, and since I've taken out the 1 over 2 mu naught, this field term just becomes B squared. So this is simply a rewriting of the energy cost of, well, the energy of a field configuration in the superconductor, where we've eliminated the supercurrents in favor of the field itself. And this illustrates my point from Wednesday's lecture about the fact that you can no longer think in weak coupling terms of these two sets of degrees of freedom, the supercurrent and the resulting field. They're strongly coupled, and so I can always eliminate one in favor of the other. And here I could just talk about the free energy based on what the field is doing. Of course, the field is doing what it's doing because it is in a superconductor which is carrying supercurrents. But we can work purely in terms of the field. sorry.
Should be able to get that just by integrating out theta, right? I think. So like Ampere's law should be implied by your free energy somehow if you were to do the variation with respect to theta.
If I had the, I'd need the F mu nu.
Well, you have the b squared, which is basically the spatial part of that, right?
Yeah, that's true. Would I need E? No, maybe I don't need E. Yeah, you're probably right. If I just integrate out the phase fluctuations, I would get this.
Yeah, so it's quadratic in theta, so I think you can.
Yeah.
And what is the temperature dependence in this expression? M star?
So we don't really have temperature dependence now because the temperature dependence came in setting NS. So it's NS really that has the temperature dependence because that's the superfluid density which is related to the modulus of the order parameter. So as I cool the system, that NS will get larger. So very near the transition, NS is very near 0, and so this factor is very large. But then very near the transition, neglecting amplitude fluctuations probably wasn't okay anyway. As I get further away from the transition, NS gets larger, so this prefactor gets smaller. Yeah.
Can you explain a little bit more how we get these supercurrents? Because I have the impression that if we are a particle in B field, what we will consider as the current will be only the gradient and not the A part in the expression of P, of the momentum.
Right.
But here it appears.
Yeah, that's right. I mean, that's related to the fact that the U1 symmetry, which is giving rise to the current, now involves changes in both theta and A. So the case you're thinking about would be when I had a U1 symmetry, which was just a sort of rephasing of the field. And so then when I looked at the current associated with that, I pick up terms that only involve the order parameter field. But now I don't have a symmetry which involves just rephasing the order parameter field. I have a symmetry which involves rephasing the order parameter field and slipping the vector potential. And so the U1 symmetry acts differently, and therefore when you go through the Noether argument, you get a different current expression.
Yeah, I mean, somehow you should be able to say that the real momentum is not just like the inertia of a particle, but like it's carried by both the charges and the electric field. The electromagnetic field also carries momentum, and that's also contained in here.
Another way to see it is that the current is whatever the vector potential couples to. And so if I expand this bracket, I'll find that the vector potential is coupled to this combination, not just to grad theta.
No, I don't understand here.
So in general, my action when I couple in a current to a vector potential is this. So whatever the vector potential couples to must be the physical current.
Okay.
And so here the vector potential is coupling to this combination. So this must be the physical current.
So one of London's original papers from the 1930s is a Nature paper where he agonizes about this, actually. So London has a paper in the 1930s where he's thinking about the analogy between a macroscopic supercurrent and an equilibrium circulation of electrons in an atom, right? Where the same thing comes up.
Okay.
Right. So you might find it interesting.
Yeah.
Excellent.
I don't quite understand what is like super about this current, because if I would just have a field theory of any complex field, it would have the exactly same action of free energy. So why is this now like a super current? So where do we use this property? Is it just because we said we have no spatial variations, or where does this enter?
So this is still a theory of a condensate. You could. How did we say that something was a supercurrent in the case of the superfluid? We argued that we had two contributions to the current, one of which was effectively an adjustment of the ground state to the boundary conditions, and the other of which was sort of entropy carrying excitation. So I'd say this is a supercurrent in the sense that it's not entropic. It's still just an adjustment of the ground state of the theory to the boundary conditions that we apply.
So in principle, in the free energy, there should have been an entropy term, right? Like for this, but this is what you're saying now.
Right, exactly. There is no entropy.
Set it to zero, and that's what makes it super.
Yeah, and I've got a lot of sympathy with this agonizing, right? Because what it means is that there's an equilibrium. What you're talking about, the entropy, right? It's an equilibrium current, right? But equilibrium currents are far more common than supercurrents. Right? I will bring in next time a piece of graphite and show you it levitating over a magnet just like a superconductor. Right, and that is due to a form of diamagnetism that you can express in terms of equilibrium currents. But if you like, they're local. They don't have this. So and the London equation actually applies to something like that as well. A London equation is not unique to a superconductor, right? But what's unique here is that it's a macroscopic equilibrium current. Right? The ones you're thinking about in atoms are in some senses microscopic. And when we hear about the length scales, when Chris derives them, we'll understand the difference. But that's the really interesting point. The characteristic of a true supercurrent isn't quite what you might have thought it was. And I did my PhD with a guy called Gil Landrich, who's one of the best physicists Europe's produced. Oh, he's American, but born in Trieste, so one of the best physicists working in Europe. And he just put it brilliantly to me. He said the first time he saw a diamagnetic object levitating over a magnet, he thought, what's going on there? So he left it, and he came back next day, and it was still there. Left it, he came back the next week, it was still there. And he thought, that's an equilibrium current, right? And so, that's really what the essence of a supercurrent is relative to the essence. And now, of course, we have far more examples of equilibrium currents because we have some things with topologically protected edge currents and things. Those are also equilibrium currents in some senses, but they aren't supercurrents.
Right.
So I think it's the macroscopic nature, and it's the fact that over the bulk of the sample, the amplitude of the order parameter, which is ultimately leading to that current, is not spatially dependent. Do you agree with that?
Yeah, perfectly happy with that. And do bring in the graphite.
I will do, yeah.
It's always a pleasure.
I keep forgetting it. It's just sitting in my rucksack in my office.
Or floating in your rucksack in your office.
Indeed.
Okay. Any other questions so far? Okay. So we're basically almost there now. We've got this effective form of the free energy where we've eliminated the phase variation of the order parameter in favour of an expression in terms of the field. And you can just see by looking at the structure of this will give me 2 powers of inverse length, which means that this prefactor must be a squared length. And so I should probably call it something. Let me call it lambda L squared. So this lambda L, which is defined as the square root of m star over 2 mu naught NSE squared, has a name, and we'll see in a moment how it gets that name. It's called the London penetration depth. So this is a second length scale in addition to the coherence length, which the superfluid already had and the superconductor also has. And it clearly represents something about the response or the behavior of the magnetic field inside a superconductor.
Why is the current is not creating its own magnetic field right now?
It is.
So
This is the magnetic. So there's only one magnetic field, B, and we're not talking at the moment about boundary conditions or putting the superconductor under any stresses, although we will talk about that. At the moment, we're just asking what is the intrinsic set of equations that describes the behavior of the magnetic field inside a superconductor. And so actually a crucial ingredient of that is that the magnetic field and the supercurrent are related by this equation. And so I can write everything in terms of the magnetic field. Other questions? Okay, so let's now ask about a particular problem. So, what does this constant with the dimensions of length that we've discovered in the equations mean? So to illustrate that, let me take the boundary of the superconductor. So this bit on the right is the superconducting sample. And let me assume that I've arranged my experiment so that outside the superconductor I have a constant magnetic field parallel to the surface. So to adopt a coordinate system, let's say that x plus x is the direction into the superconductor and z is this direction along the surface in which the field points. And what we'd like to find out is what the field does inside the superconductor subject to this boundary condition. So what we want to do is to minimize this delta F with respect to B of R subject to the statement that B at x equals 0 is some constant external field magnitude in the z direction. And the reason I've picked this simple geometry is that it seems likely that the field inside the superconductor will continue to point in the z direction and we'll just have some strength now that depends on how far we are from the surface. That would also be true if this were an ordinary metal. If this were an ordinary metal, we would find that Bz was just constant, independent of x, i.e. the field just propagates into the metal. Here we're going to find something different. So, in order to minimize, we want to vary B. So we want to add a little bit to the field and require that that should cause no variation in F. That's the usual first derivative test for a minimum. Strictly, it only finds an extremum, but there's only one solution, so then that'll be fine. So we have to think a little bit about doing that variation on this curl term. So the b squared term goes to b plus delta b all squared, which is approximately b squared plus 2b dot delta b. The curl b squared term goes to curl of b plus delta b squared, which is approximately curl of b squared plus 2 curl B dot curl delta B. And I'm just dropping terms of order higher than linear in delta B, as one always does in these things. And so the change in, I suppose strictly the change in delta F is 1 over 2 mu naught times the integral over space of lambda L squared times 2 times curl B dotted with curl of delta B plus 2B dotted with delta B. Okay so far? Now our problem is that we would like to say that this is something multiplying delta B, and so the something must vanish since delta B is arbitrary, but we have this delta B here inside the curl, so that makes this difficult. The solution to that is to integrate by parts. And that will hop the gradient onto this other side, and we'll pick up a minus sign. I'm slightly worried about that minus sign. So my notes say that integrating by parts, this term is going to become 2 lambda L squared times the curl of B plus 2B, all dotted with delta B. My momentary concern was that when I integrate by parts, I usually pick up a minus sign, but I seem to remember that the anti-symmetry around the cross product causes that to cancel in this case. So I'm going to trust my notes, because I did work this out carefully before copying the answer down, and I think this is what you get. So that then gets us an expression for the variation of the energy, and you can see then that if this is supposed to be 0, whatever I do to delta B, then the thing in the brackets must be 0. Usual derivation of equations of motion. And so that tells me that curl of B is equal to minus 1 over the London penetration depth squared times B itself. And this is actually one of London's equations. It's the second London equation, but written in gauge invariant form. And this is manifestly gauge invariant because it's written only in terms of B, which is an observable.
Just, I don't know if you have looked at much at Digen's book, but what he did in the first chapter that I like so much was this derivation, but starting without the he hadn't done A Ginsburg-Landau, so he just started with the postulate that you had a macroscopic equilibrium current.
Yeah, okay, and then you could just say we have a J.
Yeah, that's right.
Indeed. Yeah, and yeah, you can see that this is in some sense independent of the expression for J. You could just have said that the kinetic energy of a current goes like its square. Yeah, indeed.
But it had to be, you know, you made a phase transition of some unknown origin into a state that supports a microscopic persistent current. That's the only assumption I'm going to make. Here's everything that follows from it.
Yeah, exactly.
And so this equation now holds in all space, so both inside the superconductor and also outside.
It doesn't hold outside because what we did to get to it was to make this assumption that the amplitude of the superconductor isn't varying.
But then don't you have to worry about boundary terms when you integrate by parts?
You probably do in principle.
Delta V is 0 at the boundary, so I think it's okay.
The variation is fixed at the boundary.
Yeah.
Yeah, okay, because we're fitting a fixed boundary condition. Okay, I'll buy that. Okay, so that's derived what is effectively an equation of motion or an equation describing the field profile. Let's see what it tells us for this particular geometry. So we've already agreed that for this, well, I don't know whether we've agreed, I've already said that for this geometry we expect the field direction to be constant as we go into the sample, and we're imagining that only the strength will vary. So if I use the following facts, so there's a vector identity that the curl of a field is the gradient of the divergence minus the Laplacian. The divergence of the magnetic field is identically 0. That's another of Maxwell's equations. And so this London equation can be written as the Laplacian of the field is equal to plus 1 over lambda L squared times the field itself. And in this particular geometry, we're only expecting this to have a z component, and we're expecting that to depend only on x. So in this particular case, that will give us d2 bz by dx squared is 1 over lambda L squared bz. This is now an ordinary differential equation to which we can write down the solution. It's some constant times e to the x over lambda L plus some other constant times e to the minus x over lambda L. This solution is growing without limit as we go into the bulk of the superconductor, so is presumably unphysical. So let's just delete it. That gives us only a solution which is decaying as we go into the bulk of the superconductor, and then matching that constant to the external field. We get exponential decay of the external field on a length scale given by this London penetration depth. And so that's flux expulsion. We've taken our sample of superconductor, we've put it in an environment where there is a constant magnetic field parallel to its surface, and unlike an ordinary metal that would have just let that field penetrate the bulk, it is in the nature of the electrodynamics of the superconductor that it doesn't do that. It gives us a field profile that decays exponentially as we go into the sample. So we have B as a function of x, Bz as a function of x, which decays from its externally imposed value over a length scale that's given by this lambda L. Notice that since the London penetration depth goes like 1 over the square root of the superfluid density, and as the superfluid density vanishes as we move towards the critical temperature, the London penetration depth diverges as we move towards the critical temperature, and the superfluid density vanishes linearly, so this diverges like 1 over the square root. of the proximity and temperature to the transition. I note, for future reference, that that's exactly the same divergence that Ginzburg-Landau theory predicts for the coherence length. So both the penetration depth and the coherence length diverge as we approach the transition from below, and at least in this theory, they diverge in the same way. Good. Yeah.
Have to? Sorry, do they have to diverge in the same way? I mean, they could have different critical exponents somehow.
Yeah, in principle, I don't know of a deep reason why they would have to diverge in the same way. Certainly in this theory they do. It would cause a problem if they didn't for our terminology, but I don't know that it would cause a problem for the physics. But we'll talk more of that when we come to type 1 and type 2.
Can these be measured? Like, has it been verified that they diverge like in the same way?
So I know about measuring penetration depth, and there are various methods for doing that. Maybe the most direct is to take an isolated sample of your superconductor and put it in a microwave cavity. And then the resonant frequency of the cavity depends on the cavity volume, excluding the superconductor. But then as the penetration depth gets longer, the superconducting sample effectively shrinks from the point of view of the magnetic field. That changes the resonant frequency of the cavity, and then you can see that the penetration depth is going up. So that's measurable that way. Yeah.
There's a more direct way now, at least the muon guys claim. So muon spin rotation measures internal fields. And they're able to get very, very low energy muons whose implantation depth they can vary with muon energy or something. So they're able to actually measure the exponential decay of the field into a sample.
Mm-hmm. And what about the coherence length?
Well, the coherence length, as you'll tell us all soon, goes as flux quantum over 2 pi psi squared. So the upper critical field goes as 2 pi over coherent flux quantum over 2 pi psi squared. Mm-hmm. The upper critical field is essentially a measure of psi squared.
Right. Excellent. Good. Not that we've introduced upper critical fields yet, but,
I know.
But we're heading that way. Okay, so yeah, the answer is they're both measurable, and they do this. Okay, so that's our exponential decay of an externally imposed field into the bulk. And so that demonstrates that a feature of this theory with, as Andy says, the macroscopic persistent current is that it's in its nature to expel field. And the way it does it is to run currents around the edge of the sample, right? We can use Ampere's law. So how does this happen? We can use Ampere's law backwards, right, to say that J is 1 over mu naught, the curl of B. B is pointing in the Z direction, its derivative is in the X direction, which means that this current will be proportional to Y. And so that tells you that there's a current running out of the plane of the board, which is screening this magnetic field. And so it's perfectly physical. The system sets up a persistent current which runs round the boundary of the sample. The current also decays on the same length scale as we go in, of course. And that current is such as to screen the magnetic field to 0 in the interior. And because we have no dissipation, there's no resistance to that current, you don't have to keep pumping energy in to keep it going. So this is a real kind of equilibrium configuration of the system where it's adopted this current to screen out the field.
So when you set up a supercurrent, is anything really moving? I mean,
forgive me for the question I'm about to ask, but define really moving.
This is what happens when you get somebody who did a philosophy degree.
But I mean, in some sense, that's an important question, right? Because we're used in classical mechanics to the idea that if something is, we're used to two definitions of something moving being the same. One is that there's a non-zero expectation value of momentum, and the other is that something is changing with time. Those two do have to be the same thing in classical mechanics, because the only way you can have momentum is for some of your particles to be moving, and therefore something is changing with time. But in quantum mechanics, even single particle quantum mechanics, that's not true. Right? You can have plane wave configurations, e to the ikx, where the probability density is completely independent of time. But if you measure the momentum of the particles in that beam, they're all moving to the right. Right? So somehow, because you've lost this point particle thing, I can now have an infinitely long beam of particles, all of which have momentum along the beam, but without any observable changing in time. And this is like that. There's somehow the macroscopic wave function is not time dependent, but the macroscopic wave function modulus of a beam of quantum particles isn't time dependent either. And yet they're moving in the sense that there's momentum there.
If the magnetic field is about to enter the superconductor, in the sense that it's y in the x direction, for instance, then we can do all the computations the same way, but then when we do the current, we will have nothing.
So yeah, you mean if I point the magnetic field along x, then this would become d2bx by dx squared is this. We would get an exponential decay x. Yeah, and then you're saying that the current would give 0.
But well, we'll have a field, a magnetic field with divergence, non-vanishing. So yeah, it's not.
Ah, yeah, okay. So yes, right. Magnetic fields have to be transverse, and so yeah, I think you've answered your own question. Right. Yeah, I was working round to the same thing and thinking, well, how would you arrange physically a situation in which the magnetic field lines were forced to penetrate the superconductor? But yeah, I think you're right. It's a failure of the divergence-free condition then.
And so it will go around or something.
It must, I suppose.
So the things that you just have to, if you were to point it into x direction, then for consistency you also would need to change the magnetic field outside of the sample.
Right. And then, in the end, you have to define these things operationally, right? So what am I actually thinking of doing? I don't get to fix the magnetic field directly adjacent to the sample surface. I get to fix some coils, some distance from the sample, and then the magnetic field does what it will. So I guess implicit in this formulation is that this is already consistent as a potential field configuration in response to some coils somewhere. Actually, as we get onto this, let me mention something which I think is important for later discussion, which is the energy cost of expelling the field. It's not really obvious from this derivation, and it's really not discussed in the books, what the energetic competition is when a superconductor goes superconducting and expels the field. Because we wrote down that B squared term in the free energy, that was positive, right? So that makes it seem like expelling the field is always good for you. And you think, well, why don't ordinary metals do it? And so what you have to think of, let's do this now because we're going to need it later. So what you have to think of is rather, as we were just discussing, an experiment where you actually impose the field and how you do it. So this is still a cartoon, but it's a slightly better cartoon. So suppose I take a large box, and let's say that the top and bottom faces have area A, and the height is L. And let's say that I somehow experimentally fix the flux through the top and bottom of this box to a value phi. So that means that, all things being equal, I have flux lines just running through the box. I'm going to assume that edge effects are negligible, and so this just looks like a region of uniform magnetic field, and the magnetic field is the flux divided by the area. So what's the field energy? Well, it's the integral over space of b squared over 2 mu naught. B squared is phi squared over a squared. The volume is LA. And so the field energy is actually L phi squared over 2 mu naught A. So that's with vacuum inside, except for the field lines themselves. Now suppose I put a superconducting sample in, which is showing the Meissner effect. So I'm going to have the same boundary conditions. I'm going to force the same number of flux lines to enter at the bottom of the box and the same number to leave at the top. But now I'm going to have a smaller superconducting sample in here, which is just going to expel the field. So we'll get something like this. And I'm going to use a very crude cartoon image of how the field lines are expelled, which is that when they hit the surface of the superconductor, they follow it to the correct point on the opposite side and then resume. It's kind of a crude picture, but it actually works for the purpose of this calculation. So let's say that the superconducting sample has a smaller height L naught and a smaller surface area A naught. And so what we want to assess is what the field energy is now compared to what it was before we put the superconductor in. So the energy with the superconductor in can basically be thought of as coming from two zones. There's the zone below and above the superconductor, where the field line density is exactly what it was before. And there's the zone around the superconductor where, of course, the field line density is increased, because you've got the same flux, but now passing through a smaller area. So we'll always have a 1 over 2 mu naught. And now we need to do b squared in the first zone times the volume of that zone, and b squared in the second zone times the volume of that zone. So what's the magnetic field in the first zone? It's phi over A. Right? It's, according to my simplified picture, the field lines here look exactly the same as they did here. And the volume of that zone is the same area A, but now times the height of the box minus the height of the superconductor. What's the average field in the middle zone? It's 0 inside the superconductor, but not outside. I want to integrate over this area that's kind of the same height as the superconductor, but not in the superconductor.
So phi divided by A minus A naught.
Excellent. So it's the same number of field lines packed into a smaller area. So it's phi divided by A minus A naught. That gets squared and multiplied by the volume of this region, which is A minus A naught times L naught. So everything goes like phi squared. And then what do we have? We've got an L over A from the first term here, minus an L naught over A from the second term here, and then we've got plus L naught over A minus A naught. And you can already see, right, so this term is the term we had without the superconductor present. And this term is definitely larger in magnitude than this term because the denominator is smaller. So this tells you that the energy has gone up. So in other words, so there are compensating effects, right? You've reduced the volume that's carrying the field, which in principle will make the energy go down, but you've made the field stronger, which will make the energy go up. And since the field gets squared, it's the going up that wins. Now, I can make one further illustrative approximation, which is to say that if the superconductor is much smaller in area than the box, then I can approximate this as, well, it's exactly equal to 1 over A times 1 minus A naught over A inverse, and that's 1 over A plus A naught over A squared. The 1 over A cancels this bit, and so I get that E superconductor present minus E vacuum is approximately phi squared over 2 mu naught times L naught A naught over A squared. But phi squared over A squared is the original field strength. L naught A naught is the volume of the superconducting sample. So this just gets you this simple expression that the energy increase of the electromagnetic field when you plonk that superconductor in is the original field energy density times the volume of the superconductor. Which looks deceptively simple, but to me wasn't obvious. There may be some neat trick to work out that this is exactly what it must be, but I think this derivation shows that it actually depends on the fact that the energy goes quadratically on the field. So what that's telling you is that all other things being equal, kind of obviously, forcing the field lines to deviate from uniform propagation costs you energy. And it costs you an energy which goes like the square of the field strength. So if this is going to be the equilibrium configuration, there must be some energy that's balancing that. Any suggestions for what the energy is? The field energy's gone up, so some energy somewhere must have gone down.
With the condensation.
It's the condensation energy of the superconductor. the superconducting ground state has lower energy than the normal state when you're below TC. And so this is how the competition works. So if you have a superconductor sitting in the middle of a box like this with fixed field boundary conditions, at temperatures above TC, the lowest energy solution is to let the field do what it would have done anyway and have the sample be normal. At temperatures below TC, the lowest, free energy solution is to have the sample go superconducting and expel the field.
As long as the field's not a bit too big.
Right, as long as the field's not too big. And that's the point of this discussion, right? To say
You get the critical field.
precisely. So this is to point out that this is a competition between two finite energy costs. And so as you increase the field, this energy cost goes up and up and up. And so at some point, the minimum energy state is still just to make the superconductor normal and to put the field lines through it as if it were a metal.
At which point it is a metal.
Well, at which point it is a metal, indeed. Yeah, so it seems worth discussing that now, because what comes next is a discussion of how that transition happens. But I think the place to start is to appreciate that there must be such a transition, that in the end I can build up such pressure from the field lines outside the superconductor that they just force themselves in.
Sorry, I have a little question. So regarding the equations that we saw before, we saw that if we have a superconductor and then we have a field that comes parallel to the wall of the superconductor, it would go without any deformations constantly. Suppose I have a constant field. And then we saw that if I put a field like this, it will eventually decay exponentially. So according to that picture, I would expect that here, those lines of the field that come, they disappear inside and they reappear.
But the problem with this, as Benoit was, I mean, that's kind of the example that Benoit gave. And the problem with it is that that field configuration doesn't obey the Maxwell equation that says that the divergence of B has to be zero. Right? Magnetic field lines can only end on magnetic monopoles. So it is true that this equation appears to predict that, but you have to solve this equation, you have to solve the London equation together with Maxwell's equations, one of which is that the divergence of B has to vanish. So actually what that means is that before they reach the surface of the superconductor, your field lines will start to deviate. And so this thing, they'll wrap round the superconducting sample because that's the only divergence-free configuration available to them. Right? If the line can't end and it can't exist in the bulk of the superconductor, then it must be that it has to go round.
But then somehow in the equations we should see that this field is actually deviating and going to infinity asymptotically.
Which I think if we solved them together with div b equals 0, we would. So here we've done a much simpler calculation where we've written down a parameterization that always obeys div b equals 0, and then we've looked within that parameterization for a solution that obeys the London equation. But in general, for arbitrary field angles and boundary conditions, you'd have to solve the divergence-free condition and this London equation together. And yeah, I haven't proved that what that will give you is the field lines circling the superconductor and then rejoining, but it must, because if they can't end and they can't go into the superconductor, that's the only option.
I mean, ignore this question if you come back to it later, but right now it seems like there's a critical magnetic field at which everything turns normal. Mm-hmm. But it's like you have a finite penetration length, which is the same independent of the field, and then only at some point it basically everything becomes normal and it enters. Is this really what's happening, or is it like the superfluid becoming normal on the edge basically, and then
it's much more like that. So the penetration depth is also field dependent, and will increase as you increase the field towards
But I mean, from the equation that we had before, it's not field dependent, right? I mean,
Yeah, I see what you're saying. So this free energy is supposed to be good. Right, but it's only not field dependent if the superfluid density is not field dependent. And the superfluid density will be field dependent in conditions of more than small field. So it's all really wrapped up in here, but this superfluid density is actually a function of field and temperature.
It may be related to the fact that we gain energy being in the superconductivity, but if we look at the free energy that we've written, if B is constant, then if B is constant with our superconductor and in the box, in the big box, then we will have an energy which is smaller, because the curl term will vanish if B is constant.
Yes, but the alternative is to make B 0 inside the superconductor, and then this term will vanish.
Yeah, but if we consider the free energy of all our box, then this B equal to 0 inside will lead to B greater outside.
Yeah, that's right. But that's exactly where the condensation energy comes in, because if you want to put a magnetic field into the region that the superconductor occupies, then you have to make it normal. If you want to put a magnetic field into the region of space occupied by the superconductor, you have to make it normal.
But this is not here. It's not.
Well, it is, because the equation that you get from minimizing this is this London equation. And this gives you decay of magnetic fields to 0.
Maybe part of the confusion was coming from dropping, the terms that are proportional to psi squared.
Condensation energy. Yeah, indeed. So if we included those, there would be a constant here, which. So this would also have plus the volume of the sample. Let me take them as uniform. So the volume of the superconducting sample times minus A over 2 mod psi squared plus B over 4 mod psi to the 4th. And in the superconducting state, this is negative. So the choice you have basically is either you can have a non-zero modulus for this order parameter, but then in that case, your magnetic field inside obeys the London equation, the only constant solution of which is B equals 0. And so you can have this field non-zero, but then you have to have B equals 0 inside the bulk of the superconductor. Or you can have this order parameter 0, and then you can have a non-zero field inside the bulk of the superconductor. Remember that this expression was derived under the assumption that we don't have significant amplitude fluctuations of the order parameter. So the London equation and the conclusion that the field decays to 0 is a conclusion that's valid in the presence of a non-zero superfluid order parameter which is not fluctuating in amplitude. Now you could ask, are there intermediate options?
Yeah.
And actually there is an intermediate option in certain types of superconductor, which is the Abrikosov vortex lattice. But if the only two states we compare are superconductor is fully superconducting and has no magnetic field inside, versus superconductor is fully normal and has the full magnetic field inside, then the former is preferable at low fields and the latter is preferable at high fields.
I think there's also a little bit of confusion because this curl B term actually, I mean, this only is there for the superconductor. It's not there for the free field. Because
Yeah, no, that's exactly right, because this comes from the supercurrent, which can be only inside the superconductor.
And so basically we have two calculations. The first one is only the superconductor, and the second one is only outside the superconductor.
Mm-hmm. Yeah. Okay. Any other questions on the energetics?
You have another question? So in the expression that you got at the end, it was the energy difference between the superconducting and the vacuum sample is squared, and you said that this is compensated with the everybody going to the ground state, so with the condensate.
Yeah, so basically by this energy.
Which means that we can reach a condensate phase by either decreasing the temperature or increasing the magnetic field? Because if I keep increasing the magnetic field, this energy would increase proportional to B squared.
Yeah, that's right. So it's the other way round. It's that this energy has a certain maximum which it can reach,
Yep.
whereas this energy can go up without limit. And so the risk of duplicating notation. So the energy of the state where the superconductor is superconducting is the energy of the state where the superconductor is normal plus something that goes like B squared minus the condensation energy density. So let me call this condensation energy, including the VSC, E-cond. So E-cond is, so E-cond is negative. This field cost of expelling, this energy cost of expelling the field is positive. So there are two regimes, right? When the field is small, E-cond has a larger magnitude than this term. And so overall this bracket is negative, and so the ground state is where the superconductor is superconducting. That's the condensed phase. When the field gets larger, at some point this field energy will overcome the condensation energy, and then the ground state is where the superconductor is normal and the field penetrates the whole volume of the box, including the superconductor. So it's the other way round to what you said. It's that we get the condensed superconducting phase at low temperature and low fields, and we can drive the superconductor normal either by heating it or by increasing the field. Yeah. And we'll draw phase diagrams for this. Good. Any other questions? I sort of feel like it would be a mistake with 10 minutes to go to try and start doing quantization of circulation and things. So why don't we just leave it there for today, and we will reconvene next week on Wednesday, and we will talk about the fact that indeed for certain superconductors there is an intermediate option between allowing the field in and becoming normal and expelling the field and remaining superconducting, which is the creation of the Abrikosov vortex lattice. So we will describe that and when it occurs. Thanks, everyone.